So, welcome back, everyone, to Revolutionizing Healthcare, our 41st session today. And this is going to be another core concept session where we're going to be talking about LLM co-pilots and machine learning with no-code tools. And for this session, we are very excited to be joined by a couple of wonderful panelists who I'll be introducing in just a minute. Before that, this session will roughly run 1 hour. It will be structured as follows. We'll have the introduction and afterwards a presentation on a new copilot that the lab developed that builds on top of Climb, which you may know back from a session in October. Then we're gonna continue with the panel discussion and have Q&A either interspersed during the panel or at the end. That also means that you can ask questions in the Q&A chat at any time, and I will put them to the panelists whenever appropriate, or also ask you to unmute yourself and ask your question live. Without further ado, let us get to know our panel of today. First of all, we're excited to have Professor Russ Altman with us. He is the Kenneth Fong Professor of Bioengineering, Genetics, Medicine, and Biomedical Data Science and Computer Science at Stanford University. He's also a Senior Fellow at the Stanford Institute for HAI. Then we're also excited to be joined today by Professor Mary Beth Terry, who's the Executive Director at the Simon Spring Institute, an Associate Director at Herbert Irving Comprehensive Cancer Center, and a Professor of Epidemiology at Columbia University. And finally, we're really excited to have Dr. Anders Boyd with us today, who is a researcher at Stichting HIV Monitoring and a statistician at the Department of Infectious Diseases at Amsterdam UMC. And to get us started and introduce the rest of the lab team to you, I will hand over to Professor Mihaela van der Schaar, who is the creator of these sessions.
Thank you very much, Tim. Hello, everyone, and welcome, Russ, Maribeth, and Anders. What a pleasure to have the three of you talking to us today. So many of you may wonder, we just had a session in October on copilots. Why another session on copilots today? Well, we were very excited and we received a lot of positive feedback after our last session on copilots. And we realized at the same time that there are some important things missing. First, the copilot that we presented in October took relatively clean data, ingested relatively clean data, and then did a lot of magic. But we realized that a lot of the clinical data sets that clinicians, epidemiologists, biostatisticians are dealing with are actually very messy. And hence, copilots should take that into consideration. Number two, the reasoning capabilities of our previous copilot were limited. And we needed to improve this reasoning, especially since the pipeline, the analytic pipeline that needs to empower clinical researchers using such copilots is quite complicated. And finally, while we had in Climb a clinician as part of the co-authors, we didn't have somebody really that was doing analysis of biomedical data on a daily basis as a co-author. So I'm actually very excited that Anders, who is not only a panelist today, but also a co-author of this copilot, has joined us to really help us drive the vision behind building such copilots that are truly useful for people like him. So Anders, I'm going to give the floor to you and tell us about it.
Thank you so much for the warm introduction. And yeah, I'm really pleased to be presenting some very, fascinating research that we've been doing with at Mihaela from the Schaar Lab, specifically looking at this large language model Copilot and how we've advanced this further. So before I want to begin, I really want to talk about, let's talk about some context. Why is this Copilot even needed to begin with? And I'm a biostatistician, so my perspective really comes from the biostatistical angle and where I see the data coming from in the clinical world. So let's take an example. This is revolutionary healthcare. We have a revolutionary clinician here. And this clinician, they might be at a university teaching hospital in a high-income country, let's just say, But their stats background, okay, they took a course in biostatistics maybe or epidemiology. They could probably program a little bit in SAS, and they might have some sort of understanding of some machine learning tools. They come with me, or they come up with some sort of problem. And this problem is that, let's just say they're preventative cardiologists, and they've started using a different type of therapy in their department. And they're wondering, does this really work? Is this effective for cardiovascular disease prevention? What they come with is electronic medical records. They have information on the clinical aspect, so they can have an outcome data. They also have information on the treatment data as well, so they know who's been given what. And as the biostatistician, we then bring all the data together. We look at the distributions, make sure everything works. I might, run a simple descriptive graph, and then might run a simple regression, and the story ends there. So we can kind of bring an answer to that problem. Let's take a different example. We have revolutionary biologists now. We have people that are at let's just say a research institute. They look at differences in, they look specifically at microbiome dysbiosis, and they have amazing technology that looks at this. And they really like to focus this on chronic diseases. Their stats background is a little bit limited. They're mostly biologists. In fact, they could probably help from some bioinformaticians, but these are mostly outsourced. They've heard of machine learning probably from different colleagues, but once again, this is not their main stay. They come with a different problem. They have this new technique that looks at various different taxa. There are various different families, even a broader range. And then what they want to know is they also have patients that are looking at different stages of cancer. And what they want to know is, okay, are there differences in the microbiome at different stages of cancer? What they have is high dimensional output. And they also have clinical data that allows us to address this question. Once again, here comes the biostatistician. We bring the data together, we look at distributions, we might run a heat map, we might run a network analysis or something different to look at how to try to help explain the data and see if there are really differences in microbiome across the stages of cancer. Now, in this third last example, let's pretend we have a revolutionary epidemiologist. And let's say they come from a non-governmental organization and they specifically looked at health crises. And the issue really here is, well, not really an issue, but they have personnel that really focus on the response, the response to that crisis. And they do a lot of investigations, but they don't really publish it oftentimes. And they do have some understanding about machine learning tools. And let's just say they have an issue. They have a loss of virus that comes out. And individuals suspected, and let's just say confirmed loss of virus. And what they want to know are there clinical predictors that are associated with mortality? What they possess is different clinical and laboratory data, and this was specifically collected during outbreaks. This is very rare data. Once again, they come to the biostatistician, we bring the data together. I might run some sort of time series analysis. I might do some regression analysis. But once again, we want to answer this research question. So what do all three of these type of problems all have in common? Well, we start with the revolutionary healthcare researcher, and this starts at the clinic. Now, as you notice here, we have diverse backgrounds. We have diverse statistical knowledge. And one thing they all share in common is that they have this desire to understand their research question. In fact, this is what we do. At the end of the day, we really want to help our patient out. What they bring to the table is data. They bring a research question and they bring motivation. So as we drift to the biostatistician or the research angle, the major actor here really is the biostatistician, the epidemiologist, or maybe the clinician that knows more about statistics. What we try to do is we try to translate that research question into some sort of statistical way we can test this or some statistical terms. In order to do that, we have to do extensive data management, and we also have to do statistical analysis. These last two steps really take a lot of time. And in France, they have a word for it. It's called chronophage. It takes a lot of time to do these types of steps. So is there a way where you can simplify both data management and statistical analysis? So if any of you remembered Climb was definitely great for the statistical analysis, but let's bring data management into this. So now we have Climb DC. This is a tool that really combines advanced data-centric tools with large language model-driven reasoning. And it includes in the statistical analysis sets, both the classic statistical models and machine learning models, and with specific tools that will help with interpretability, because machine learning can be difficult to interpret from time to time, and also some visualization tools. And really, we are the persons that are at the center of this. We are the ones that are controlling the data management and controlling the statistical analysis being shown. How does this work exactly? Well, we have various inputs. For example, we have a local data set that we use from the clinic. We have public or non-public data sets. Or perhaps we have even an article with information on a specific study. We can all bring this in to the Copilot through natural language, and we communicate with this. We are the human in the loop. What we can generate is we can generate the data sets that allow us to do the analysis, all the data management. We can also do the statistical analysis with data description and analysis. And it also generates, in this case, it's the Python. Soon we'll get the R code out, but it gives you code that allows you to ensure that your data are, that the steps you're doing are reliable. And then finally, it gives you a certain reports that will describe all the steps that you did during your session. So what does this interface look like? It's very similar to Climb, but a little upgraded. It's also, if anyone's used ChatGPT, it's a very similar type of kind of interface. What we have here is a place where we can manage the session itself. And then we also have a place that allows us to understand the session dashboard, where we have our working directory contents. We can understand what we're doing with our project. We can even look at various data transformation tracking. We also have a session an interface that allows us to communicate with ClimbDC, and we also have a session record which allows us to look at relevant interactive diagrams and allows us to use certain tools and code execution outputs. So this is really what the interface looks like, and we'll soon see enough with Evgeny, who will be co-presenting with me, specific issues that when we with the Copilot itself. One thing I want to mention here is that we are using patient data, and of course, a lot of patient organizations say, okay, you're using AI for my data. That's really quite concerning for me. Is this going up in a cloud somewhere, and is this going to come back in other various facets when in other AI models or large language models? So to understand this a little more, we need to look exactly how we incorporate data privacy controls in the ClimbDC. Here we have a local machine that we're using. This is where ClimbDC is located. And we interact with things like the cloud and large language model. And for this instance, what we do is we use OpenAI services from Microsoft, and we also use a large language model that's GPT-4 Turbo. But when we do these interactions, it's important to note that all the messages, all the things that are not available to other customers, they're not available to OpenAI. They're not used to improve OpenAI models. They're not used to train, retrain, or improve models. Basically, none of this is going to be used in any interface that will breach privacy, which is an incredibly important point. And when we talk about data storage, it's very minimal, and it's only related to, I guess, various aspects of the program itself. It's encrypted, and it can be deleted at any time. So I really want to bring this as a very important point. So now that I've stated about this, let's see ClimbDC in action. So what Evgeny is going to do is he's going to present an analysis that he constructed using data from a recent publication, well, not too recent, but a fairly recent publication on COVID and mortality that was published in Lancet Global Health. And of course, this is mock data, it's synthetic data, so it's not the actual data itself. We also spiced it up by including some, I guess, various facets and difficulties with data management in there. What we're going to do is we're going to walk through a classic example of how, when we use biostatistical research. We're going to do some data management. We're going to merge some files together, and we're going to try to remove useless variables, examine missingness, and we're also going to try to impute some missing data. But sometimes we can, missing data, we have our classic methods, but maybe we can use some machine learning model in here. So we're embedding in machine learning models in here. Now we can also start describing the data. We can use exploratory data analysis. We can do that classic table one the clinicians know so well. We're using descriptive statistics. And then finally, when we do our statistical analysis, we have some simple survival analysis like Kaplan-Meier curves or Cox proportional hazards model. And I don't know if any of you clinicians had the same experience, but sometimes we use these classic models and we get a reviewer back that says, well, why don't you use a machine learning model? And is the machine learning model better? Well, what we have here is a Climb gives you a nice, sometimes they're very difficult to program models, and ClimbDC gives you a nice interface that allows you to bring in those machine models to use them. And so we'll look at feature importance plots. We'll also be able to compare different modeling performances with this interface. And I'm going to give the floor now to Evgeny, who's going to demonstrate all these steps using ClimbDC.
Hello, everyone. I'm Evgeny. I'm the co-author on the paper and the research engineer behind this tool. Let me now share the screen so we can see. Fantastic. So as Anders has mentioned, we will go through a number of parts of this typical research and data management pipeline. We will use a data set that is based on the Brazil COVID data set, but we have introduced some additional data issues to it and some semi-synthetic additional things like text records just to spice it up. And I will occasionally pause and Anders will come back and give a bit more context on what is going on. So first of all, the first part is going to be data management. So let us imagine this scenario, right? We are a clinician who wants to work with this COVID data set. You can see that there are, first of all, two files, right? A primary file and the comorbidities file, and they're separate. The files can be linked through this thing called PID, which is patient ID. There's a variety of different features for different patients. And if you look, interestingly enough, some, of course, features are kind of have a lot of missing data, such as occupation, SES index, medical notes, and some have various artifacts of data entry. So there are lowercase null, NA, etc., messy values, just like you'd expect in a real data. What we're going to do is we're going to try to do survival analysis on the mortality on this is dead column and using the time column of days hospital to outcome. And of course, we can see here the various patient IDs. We have about 7,000 patients in our main data set. But as often happens in real life, we have actually a second data set which has additional data points, in this case, comorbidities, and it has a lot more records, and not of them are actually matching with the previous data set, right? So there's a difficulty there. We need to join the files. So we start our Climb DC session, and the system asks us whether we have our files in CSV and whether we have multiple files that we want to join. We say yes and yes. So we have two files, and here we go. We upload those two files, right? And once they're uploaded, now the system is asking us, is there some kind of a unique key column by which we might be able to merge those two files together? Because, of course, we have two files and we want to consolidate everything together before proceeding. In Climb DC, there's because there is the kind of a interface on the right, the dashboard, you can actually preview the files and you could quite easily figure out, oh, yes, I have this PID column. But we can actually leverage the kind of intelligence of large language models and say, oh, well, actually, I'm unsure. Could you help me? And it will actually try to figure it out on its own. So we'll write some code. The key point is here, if we go back, we see that it says that, well, let's examine the columns found in each data set. It writes the code to do that. And it looks at the column names. And then it says, oh, I figured out that probably it's going to be this PID column. Let me now write code that will join these data sets together for you straight away. And so it's done that. And we can have a look on the right, that now we have all of these columns in just one data set together. It also mentioned for us that, we lost some number of rows and there's some non-value introduced. Are you happy? So I wanted to say, well, I don't want to lose any columns from this primary file. Could you check how many rows were lost? And it will generate code and check, we didn't lose any rows. And then you as a user can be quite confident that that is good. It has merged the two files correctly, as we would expect. And here we have our final file that has all the columns from both of those initially separate files. Another thing, of course, you might quite often do is get rid of some columns that you don't need for lower next step analysis. So we have a check for that. So here's the system is asking, is there any column that you would like to remove? So of course, you can remove as many as you want, depending on your needs. But in this case, I said, well, let's get rid of that ID column, right? PID, we don't need it for our analysis anymore. And so the system immediately writes us a code to get rid of that column. As you can see, that PID column is no longer there. It's not going to pollute our results with strange things anymore. And we can even track the changes that were made to our data set. You can see that it says columns removed, PID. So we have a very, very kind of a transparent interface here that really allows you to track what is going on. So this was the section on essentially data management. Before we move on to data quality, Anders, any comments about this bit?
Yeah, I really have to, obviously we went very quickly on this, but I think we have a lot of tedious, very time-consuming steps here. And what's nice is that you can kind of see, for example, like IDs and things like that, sometimes they get lost and we're not exactly sure what is what. And what's nice is that this kind of helps guide us understand some of the data, and it's really quite an easy interface to use. What's also nice is that you probably notice Evgeny is also checking the data, and it's really a communicative partner. He's checking the data and then asking questions. Are there issues that might be coming up here? And then saying, well, what's wrong with this data? So it's really nice because with that interface, you're kind of communicating you're starting to understand your data, and you're also being an active member of understanding your data. So yeah.
Yes, thank you, Anders. So let's move on to the next step, which is all about getting your data to a good enough level of quality so we can then work on the statistical analysis later. So one thing that you would need is, of course, some initial overview of what the data is like, so both yourself and the system know what is going on. So this would be done through a cool tool called EDA, Exploratory Data Analysis. It will print out things like what are the different column names and their types, what are the numerical columns, which numerical columns actually represent categorical values, what are the different categorical values. I have a lot of different ones here, for example, different text values and so on. It looks at how many missing values there are. And it also will check for us what are the correlations in the data already, and even produce something called a correlogram. And the good thing about Climb is that it actually gives us a description of anything that it produced. So for example, we'll explain what is a correlogram and what does it represent. And then we can use this information down the line in our analysis together with this tool as a partner. Then it will use the large language model's capabilities to summarize all of those findings in a much more readable way. And then we can move on to dealing with the first big problem, which is missing data. Generally speaking, you want to not have missing data before you start doing statistical analysis tasks. So the system, based on the results of this exploratory data analysis, is asking us, so these columns have missing values. Do you think there are some strange values, such as a result of a data input artifacts, that actually represent missing values and should be cleaned up? So if we look at this medical records column here, we have proper missing values indicated with this gray none, but then there are also values that are obviously missing. There's no records there, but people have entered a dash or they entered something like none, and these kinds of things are very much common in practice. So we need to clean this up before we can even do anything like imputing the missing data. So that's why Klein will talk with you here and discuss this problem. So say, well, we think there are such missing value indicators in this medical record field. Could you list out for us the short text values that exist in that column? And then I'll tell you which ones of those should actually be replaced with need to be formatted to be properly missing values. So very dynamic. I'm asking the tool kind of questions which are just relevant to me this time, might not be relevant tomorrow. But here it shows it to us right here. There are these short values there, none and dash. So I would say, great, yes, we need to sanitize this. We need to convert this to proper missing value representation. So let's do that. And the tool, the system will write us a code to perform this processing, and we can then preview the data. And if we now have a look at the medical notes, you see that those little values are no longer there. So it's either completely clearly missing, or we have proper medical notes text. Beyond that, we now need to finally check, okay, let us try to either drop or impute missing values. So Climb has printed out to us for each column what percentage of values are actually missing. And we can see that there are a few columns which are very, very heavily missing, right? So it's medical notes, occupation, and social economic status. It will suggest that, if it's more than like 80%, we should probably consider dropping such columns before we do analysis. And we, as a user, are free to make a choice. But here we decide to, okay, let us indeed drop those heavily missing columns. The final step before we can proceed, and here is actually, in fact, once again, the confirmation that the columns that were dropped, you can track clearly that at this step, we dropped these columns. They're no longer with us. The final step is to get rid of the final few missing values that we have. We have about 65%, 0.65% of values that are still missing. So we can either drop the patients and not use those patients, or we can use an imputation tool to handle those cases. In this case, we decide to use an imputation tool. We'll use something called HyperImpute, which is a machine learning-based automated imputation tool, and it will use various approaches and find the best approach for you, including ICE, MICE, and even modern mean imputation. So the tool has been invoked, and we can see that in the beginning, we do have, you will see a few values that are missing. You can see 22 in this column, 21 in the other. By the end of this tool, of course, values should be imputed, like so, and the system will double check that indeed everything has been completely dealt with. 70 missing values have been imputed. Let us double check that that indeed has been done. Let's show per column percentage of missing values again, and we see it's all zero. So now we're happy, and we can move on to next step. So before we move on, Anders, if you want to comment on anything in this step.
And once again, what's really cool about this is it's interactive. So once again, it's giving you suggestions. Maybe you should look at this. Maybe you should do this. And then it gives you opportunities to kind of continue through the data quality pipeline. Also, what's nice is that, there is a way of, data quality sometimes takes a lot of different steps. Here, a lot of it's automated, I guess, but gives you a full comprehensive list of data quality issues, which you can kind of like sift through, and it's really quite handy in that respect. So yeah, I really do like, once again, this interactive feature that guides you through the data management process.
Thank you, Anders. That's fantastic. Well, the next thing would be more about describing the data and really learning more about our data. So there's a step called descriptive statistics. And we can see here that the CLIMB system has immediately started making the so-called table 1 for us. And not just that, it will, of course, produce all the standard distribution diagrams for each of the different features. So this right here, you can see is a classic table 1 type description of the data. When it's categorical values, it will show how many values of each category. And when it's numerical, it'll show you a range. Here you see the various plots. And again, this depends on whether your value is categorical or just continuous numerical. Show different charts. All the charts, all the plots are actually also saved in your local directory on your computer. You can check them at any time. And the final good thing is that it will actually tell you, well, I think, as a large language model, that these particular features are quite important, so you should definitely double check those. And that's contextual based on its understanding of your data. So here, for this task, it'll show us an age distribution and days hospital to outcome and mortality, which obviously this is your target value anyway, and the age group 40 to 50, and the regions are likely to be important. You can review all of that and discuss it with the system in more detail as needed. Now, because we're doing a survival analysis, it has contextually and through the reasoning and planning process grokked that, yes, we might want to plot some Kaplan-Meier plots here based on the raw data. And so it asks us, would you like to see the KM plot? And we say yes, and it's asking which columns to use. But I say, well, we earlier discussed those columns already. Just use that. Just use your understanding. And indeed, the system is able to dynamically generate some code and show us the survival KM plot for our particular data set, like so. Anything, Anders, to add, or shall we move on?
No, let's move on. Yeah, it's very good. Thank you.
And of course, now we're moving on to statistical analysis, or people might call it the modeling step. And as I mentioned earlier, what we're trying to do in this example is predict mortality, the is dead column, based on the time period, which is the number of days in hospital. We will invoke an automated machine learning tool called autoprognosis, which will use ensembles of multiple different models, including more traditional ones like CoxPH, but also neural network-based ones like DeepHit. And it will find the best performing combination of models or an ensemble for our data. It will then summarize all of the results, all of the different performance indicators. You can see it here. So just to confirm, so this is the tool that gets used in this case, so autoprognosis survival analysis. These are the classes of models that will be tested, CoxPH and DeepHit. It will try multiple rounds. It will create an ensemble, and then it will report all the different metrics. And here, the good thing also is that if you're not familiar with all the different types of metrics, there's a very clear explanation of what does each metric mean. So of course, for survival, C-index and BRIA score is something that is quite key. And there are also some additional metrics reported as well. But the final metrics are here presented for you by the large language model, and they're summarized. Note also that the model file, the statistical model or machine learning model was saved, and all the predictions were also saved on your computer after this step. Now, a machine learning model is good and advanced and powerful, but they're often hard to interpret. Right? One thing that we can do to improve interpretability is to see the feature importances, which particular features, that is columns, right, or variables, were most important when the autoprognosis model was making predictions. And we can work with the CLIMB tool to produce this exact feature importance values for us. So here on this chart, you can see from the top going down towards the bottom, from the most important variables to less important variables. And you can see that, for example, age and SpO2 were very important for COVID mortality, which of course seems to make sense, which is good. This is a very important step to get transparent understanding of your model. Now, another thing is, well, could we compare this advanced machine learning model from autoprognosis with something much simpler, which is just a plain vanilla Cox-PH? Indeed, we can do that, and Climb will train a basic Cox-PH model and compute different metrics, and even construct KM curves for us for both approaches. So that is, in blue here is the actual data's KM plot, in orange is autoprognosis, and in red is just simple Cox-PH. And you can compare those visually and reason about those. And also, large language models will tell you its opinion, but based on the metrics, including C-index and Bria score, and based on the information in the plot, it thinks that overall, the autoprognosis model is a better performing model for this dataset. But then the one final thing that everyone would, of course, would want to do with a tool something like this is to have a final record, a final report from everything, and that's where the session report comes in. And to do that, we just push this button, and that will generate for us a PDF report with all the necessary information, everything traced exactly every single step we took, all the different tools that were invoked, all the different charts that were generated at different steps, all the code that was generated and executed, etc. And you can always refer to that as in a PDF file. And that is all.
Thank you so much for the example. So one thing I really like about this method is this Climb DC really is that it allows machine learning models to be more easily executed. Oftentimes, for non-technical experts, it's really hard to run these models. Sometimes we're not exactly sure what type of program we need, or sometimes people might not program in Python at all. What's nice is that this Climb DC really brings those models in a much user-friendly interface. But of course, Climb DC does a lot more than just what we just showed today. It does a number of different data management techniques, which include harmonization, looking at feature redundancy, and also a lot of different machine learning types of data management tasks. In terms of statistical analysis, it also does a lot with subgroup analysis and subgroup challenges, very poignant, very technical machine learning methods, looking at data shifts as well as data imbalances and data characterizations. And really, what we like to say here is, what also is important to note is that these types of tools, there's so many tools out there, it's all kind of put up in in this type of library that we use. We also invite others to really bring their tools into this interface and allow us to collaborate with the Copilot, because the more and more tools that are allowed, the more capacity that we can do to really build on not only data management, also statistical analysis. Also, one last thing to mention is that really, every single individual has a different type of certain things they want to use, specific things they really want to get out of the Copilot. And what we really want to do is enhance the user experience by, developing these types of profiles so that we can really adapt the experience to the revolutionary clinician, to the revolutionary biologist, to the revolutionary epidemiologist for their specific uses. And with that, I'd like to thank a lot of the people that we've had discussions with on this specific topic, particularly with Microsoft, as well as Cystic Fibrosis Trust, who supported Nabil. And just to let you know, the publication is up on archive, so go ahead and check it out in the link below. I also am not a good graphic artist, so I use some icons. These are all the people's names of the icons that I used. So without further ado, I give the floor back to you, Mihaela.
Russ and Beth, I'm so delighted to have you with us. So Russ, if you could design the ideal AI copilot, and you are one of the very few people of the world that has both the medical and the AI in one brain. So with your brain, if you could design the ideal AI copilot for clinical research, for an ecosystem like Stanford, but more generally for the world, what capabilities would you add and why?
Yeah, so first of all, congratulations to the team. That's a very intriguing tool. And so I just wanted to say that, because in case I say anything critical, I want to be very clear that in general, this is a big, important step. I think there are questions about the assumptions of the user that we have to think very carefully about, like to make sure we don't drop somebody into an environment that they feel overwhelmed by. But let's assume we do that. This is very powerful because many of the what we call data wrangling issues that that hurt the morale of researchers because of the chronophage, because of the amount of time spent to do this work, and that would be extremely valuable for students and trainees. I think realistically, PIs never really do this unless they're young. But it would be very fun to have these tools available. The one thing that I wanted, and Evgeny mentioned at the very end, is that he said he could generate a report at the very end. I couldn't tell if that report is being done on the fly, but I had a strong desire to have another panel that was showing me my methods section as I do the methods, including things like tried, what's the name of the tool? Tried autoprognosis, didn't work. And of course, we would delete that from the paper. But I kept thinking about this is probably going to happen in several sessions. And we all know that when you walk away and have a cup of coffee or go to lunch, you come back like, where was I? What was I doing? What was I thinking when I made these decisions? So I think that that report is very powerful, and I would elevate it in the user interface because I think it's a roadmap for like where I've been and where I'm going in this analysis. And I think I think my students would constantly be referring to that as they make the decisions about the next phase, especially when there's forks. They might want to unwind the fork and say, okay, that was a disaster. We're going to try something else. And so I think that there's an opportunity for visualization of the session that would be both for remembering what you're doing and seeing how your methods are starting to look in terms of when you write them up and stuff. I could say many more things, but that was my strongest impression. And you're so close to it.
Russ, thank you very much for that. And in full disclosure, Russ and I are starting to discuss to become full collaborators. And but we didn't choreograph this. Russ, we have implemented that. What you wanted, we have done. So I won't let Evgeny talk too much about that, but we have done some of that because we feel the frustration. It's exactly what happened to us, including the fact that things crashed at times.
Fantastic, fantastic.
So, Mary-Beth, I don't know whether your audio improved.
I hope I fixed it. Can you hear me? Yeah.
Yes, we can hear you. Wonderful to have you with us.
I have two jobs, and I just got to Boston from New York City this morning, and I didn't plug in the right thing, but anyway, I thought that was fantastic. So thank you so much for that demonstration. I was really super excited that in the chat, it seems like this is a free tool for academics, because I definitely want to have our team try it out. I wanted to ask about two areas first, and then I know there's a lot of questions in the chat that are kind of overlapping with some of the questions I had, but one, you talk about sort of how you deal with missing data. If you could talk a little bit more, because especially clinically, individuals that we're missing data on are really never kind of missing at random. And it has some real issues with how, AI might be trained, and particularly in thinking about health equity and who's missing when we build these analyses. Can you just talk a little bit about that? And then my second question was, because I didn't catch it, I know you said you can do natural language processing, but I think in the example, you didn't give us an example where the notes were used, because I know with some colleagues in bioinformatics, some of their work that's been game-changing at the clinic has been when they've been able to incorporate like the nurse's notes through natural language processing. So if you could talk about those 2 points, one, when it's not missing at random, and also just the natural language processing and how that's brought in.
Pretty much, Mary-Beth, but the roles are reversed. We ask you tough questions, but now you are asking us tough questions. So you reverse the roles on me. So I'm going to take that one, but I'm going then to go back to Russ. And next time I'm coming to you, I'm going to be afraid of your question, because your answer, because it will be a homework to us. But just very briefly, since there is so much interest in missing data, this Copilot is actually building a lot of algorithms into it, as Anders has said. So it contains statistical methods such as mice, such as expectation maximization, but it contains also cutting edge machine learning methods that are ensemble methods, such as hyperimpute, which is really state of the art and contains not only statistical methods, but also machine learning methods. However, that being said, what we hope that this will happen, that it will happen, is that people who are working in there of missing data imputation are going to contribute their valuable tools to the Copilot, such that whenever somebody uses this Copilot, those tools will be invoked. That's number one. Number two, it is in the end, this is what's good about this Copilot. It is in the end in the power of the researcher, the clinical researcher doing this analysis. If they know that certain types of data has informative missingness, then suddenly what is becoming very important is for this researcher to contain that information and play with this Copilot to be able to really deal with the data based on their knowledge. So because it's due to natural language processing, a lot of the routines that necessarily are not existing in Climb, they could be built automatically using the capabilities of large language models. So I think that that's exciting. With respect to dealing with nodes, no, we do not now deal with nodes. So we hope
Mihaela, we do. We added, we added the tool in the for latest paper where it does deal with nodes.
So it's better than I thought. Thank you for that. Okay, let me go to Russ and throw to him one more question. Now, really, if we would have looking ahead, let's say 5 years ahead, let's not look more than 5 years because the world is changing so far in AI, but looking 5 years ahead, where do you see, well, how do you foresee the role of these AI copilots, both in the clinical research and the epidemiological research? Where do you see them going? And what type of tasks they should do that are big and bold?
Yeah, so I already mentioned that the data wrangling is a soul-sucking experience. And so if we can have help on that, you win friends and influence people. Everyone, it will become part of the infrastructure of biomedical science that everybody needs to learn, everybody needs to use. It's a first-year graduate student course in using copilots in effective ways. And I think that would just raise the bar and accelerate discovery remarkably. You could imagine developing classic workflows because like there are many people working on the same data set. Think about the biobanks, UK Biobank, others, where once you do a successful run, you're going to want to publish that as a service to your colleagues. So I think this can become part of the infrastructure of biomedical research. It does mean that you need to partner with these big data vendors, like partner with the UK Biobank, partner with all of us, partner with the Finnish system so that they are ready to rumble. Also, I must say that there's a move, especially in genomic medicine, there's a move to you go to their computers. So we also have to solve these problems of how do we install Climb DC on all of these compute environments where you're not allowed to take the data out anymore. It's not like when I was young. So all my students are logging into UK Biobank. They're logging into all of us. They're logging into our collaborators or drug companies' cloud, and they are not allowed to take the data out. So we need to bring these tools to the data. But that's a great opportunity because then once you've done an analysis, you can publish that, put your name on it. You can even get citations and et cetera, academic credit for doing a good job at imputing the missing data in data set X or Y. So I think it has to become part of the infrastructure. We have to go beyond SAS and MATLAB and R to the next level where maybe Climb DC is a mandatory, and of course there'll be competitors, but you need to learn at least one of them in order to be an effective scientist.
As always, Russ, you inspire me to ask something very different, but I'll have this question to you, and then I'm very keen to hear what Beth thinks about the same question.
I'll keep my answer short, I promise.
So you are envisioning this future where this maybe infrastructure has modules like that. Do you envision also a change in the way we do research? Because maybe I'm a machine learner who is interested in solving the problem that Beth has said, data not missing at random, which is interesting from a machine learning point of view. But then maybe there is somebody, a clinical researcher that has a research question, and maybe as part of these copilots, we are pulling together entire teams of experts that could integrate their expertise with a copilot, and we can end up writing maybe papers together from very different disciplines, even though we don't know each other. Do you see that things like that could happen?
So let me say that's very exciting, and I might think of that as version 2, but I think your instinct is correct that with a common platform, the platform will have the ability to find people who are doing complementary work and maybe link them where the platform becomes the common lingua franca that allows them to talk to one another. We have to be very sensitive about human interactions, and like we can't just introduce people willy-nilly. But I do think that there could be a social network on top of Climb DC that changes the way we meet our collaborators and changes the way we negotiate tasks and obligations and responsibilities during collaborations.
Almost like a matchmaking game, because I think that what's very difficult for us, the machine learning researchers, is at times to find the interesting machine learning problem to solve, and vice versa. I think the other part, the clinical world, is interested in solving these problems. I don't know, Beth, do you want to say something else about the future of where these copilots could go in your view and in your area?
Right. So in cancer, a lot of AI is really focused a lot on bringing in medical imaging, which sounds like that's already kind of a data set that could be brought in quite easily. I agree with Russ in terms of, I love the idea of having training done. For example, I had a class at Columbia that all the medical students had to learn R, and if they didn't really have to learn R and they could just use this platform, I think they would be much more quantitatively savvy. But in any event, I think with having this platform that everybody can sort of sit around a virtual table, that could also be really good for hypothesis generating. I think you could even make an argument for having sort of patient advocates at the table as well as community health advocates, because they can sit there and you can show them the graphs, and then that could be kind of the best way. I know with colleagues, that's how we use all of us data, is we show them the data and they can play with the visual screen. So I like this idea that the results come out so quickly that it's useful to show people and get people with different disciplines talking to each other. I think what we didn't address is like clinically maybe how this could be used. And I know one of the big frustrations clinically is that most of the risk models for cancer still take a while to run, and clinicians sometimes don't have the time to put in all the inputs. So to have something like this where a patient could see how their risk would be lowered if they were to do X, Y, Z, and make comparative plots for certain medications versus certain lifestyle differences, I think that would be really great. I know there's a question in the chat, and so when you get to it, I'd be very interested in how you're going to deal with the genomic data, because that always has been kind of the hardest issue with privacy. So I think you'll get to that. I'd like to kind of hear more about that. And then, yeah, I would just echo what Russ said, like this could be very useful for all of us in those kind of data banks, but you have to log into those systems right now. So finding a way where this can be put into that system would be really useful.
Both of you touched on something that I want to go back and ask, partially because I think Tim Schubert will be very upset if I don't ask, or maybe I'm cutting you, Tim. You may want to ask such a question, but since he's an MD PhD student, he often is very passionate about education and how the education in the medical schools should change given AI. Where do you see, both of you talked a little bit about that, but maybe Russ, I'm going back to you. Where do you see a place like Stanford, but more generally outside Stanford, and then Beth, you at Columbia and outside Columbia, how do you see this type of tools being developed for specific programs? How would you see them being used in a cohesive way? Would every class have its own pilot? How do you see this growing such that indeed medical education can bring some of these AI tools to the forefront?
I have to say that cracking into medical education is the hardest egg to crack because it is so highly regulated, at least in the US. The curriculum is negotiated across all the medical schools and all the experts in the different specialties. And I can tell you that even getting 1 hour of the medical student's time over 4 years is extremely difficult. So I would say that that is not the first battle to fight. The first battle is with the graduate students and getting it into their hands, where I can imagine an epidemiology co-pilot, where the principles of epidemiology are privileged and where the core algorithms are from epidemiology, which would be very different from the machine learning one. They could talk to one another, and in fact, maybe all the co-pilots have the same tools, but the way you present them and the way you prioritize them might change based on the disciplinary training that's happening. I think if you can win the hearts of the PhD students, including the MD PhD students, then medical students, it will never be part of the normal medical, I should not say never. It is very hard to imagine having something this technical be part of the routine medical school curriculum. Never say never. But many medical students get involved in research, and when they get involved in research, they will immediately love that this exists. And that's how they will learn it. And then they'll take that forward as they become fellows doing research or faculty. So I do like the idea of specialization, because when I teach, I want the tools that I know best to be privileged. And so the other question I had, and I don't think we can talk about it right now, was how do you make sure that somebody knows what autoprognosis is and that they use it in a responsible way? And so there's a whole bunch of stuff there that needs to be, I'm sure you thought about it, that needs to be addressed in terms of giving them power tools and not letting them cut their arms off.
Beth, any short last minute feedback such that we have time to answer questions, including the genomics one?
So just a comment, I agree with Russ, unless it's on the medical boards, it's hard to get into the medical curriculum. But I see this, again, it's the pro-con of whether or not AI is going to make things more equitable or it will increase the inequities that we have in our healthcare system. On the side of making it more equitable, we work all the time with the public hospitals in New York City, and there the data management challenges are really very time consuming, but also the medical doctors at the public hospital have zero time to do research, but they have a ton of fabulous hypotheses. So if they can sit down with a tool like this, I think it would make certainly for identifying patients that have more issues to focus on, and identifying precision medicine in terms of thinking about who needs more care, who doesn't. In the public hospitals, I would see this as being a real game changer.
Thank you both very much. Tim, questions from the audience. And I guess we have a question about genomics. And Evgeny, I think you need to explain how many data fields. So there's not a problem, the fact that it's genomic data, even though, of course, one could add a lot of specific genomic tools, which the tool currently does not include. So that's more on the tool side, on the algorithm side. But again, the question of how big could these tables be?
So this always depends on also how powerful your computer is. It's not just as simple of a question. If you have a reasonably powerful, let's say, workstation machine, we can be talking about hundreds of thousands of patients and tens to low hundreds of columns, and it will run in reasonable time.
Thank you, Evgeny. And I think one other question that we had in the chat, and also thank you, Evgeny, for already answering a lot of them in the chat itself. Another question was, as the system is still using LLMs, how can you sort of prevent it from making mistakes? I think this is a question that's helpful to also answer live.
So would you like me to take it?
Yeah, sure.
So how the problems with LLMs, we're talking about making mistakes and hallucinations, things like that. Yeah. So we focused a lot on kind of avoiding these problems in the design of Climb. Unfortunately, large language models are always kind of stochastic and somewhat random. So you always do need to at least slightly kind of sense check what's going on. But we use a lot of techniques like reflection and chain of thought and breaking tasks down into different, like coordinator versus planner agent. And where it's really complex, we use a tool, and the tool is code that has been pre-written and kind of debugged by us. So all of these things together significantly improve upon on just like asking an LLM to do everything. Because that way it makes way more mistakes. Using our approach, it's significantly improved.
And Evgeny, maybe also we should reiterate the fact that you are in control, you the person co-piloting, so you can see step by step. And exactly as Russ said early on, you can backtrack. You can say, I'm satisfied with the sanity check up to this point. From here on, either I don't trust, or I would like to an additional algorithm or a related algorithm to be invoked.
Thank you both. And I think we've covered most of the questions that were in the chat, either in the chat itself or now live, and we're also nearing the end of the session. So I would like to give the floor back to the panel for one final statement on basically, maybe a good question would be, how do you see a future healthcare system where you have AI co-pilots integrated in some shape or form? And maybe Professor Terry, I would start with you, and then we can go to Professor Altman, and maybe back to Mihaela. And then I will introduce the next sessions, and we will conclude for the day. So Professor Terry, the floor is yours.
Right. So I'm excited about it from a research perspective, but I can see it also being a game changer at the clinic if you can, in real time, give a patient information based on longitudinal data from their medical records. So I think if that could be done, I think you lose a lot when you don't explain to the patient right away what's going on and how they can change their risk going forward. So if something can be done in real time, I think that could really change their prognosis.
Thank you.
I was going to say something very similar, that we haven't talked about the use of the same technology for a practicing physician in the clinic. But I think patient communication, exactly as Professor Terry just said, could be revolutionized by showing them personalized plots in real time about their data. Look, your cholesterol is responding beautifully, but your sugars are still out of whack. So those kinds of conversations, and in a funny way, it would be a much easier system to build. I think the user interface would be harder, but technically, you don't need Cox, you don't need Kaplan-Meier, you don't need imputation. Well, maybe a little imputation, but the point is, the tools that a physician uses at the bedside or at the clinic would be very simple, but they could be very much appreciated. So I think there's a whole climb opportunity in helping physicians look at the medical record in real time with their patients sitting next to them.
Maybe since Tim invited me to respond, I think this is a great idea. I think that there is nothing that prevents that from happening, but there is a problem: regulation. One thing is to put something at the bedside where you would need to go maybe through a clinical trial or a device certification. Something else is to put tools like that in the hands of the researchers. So if you look back, Russ, a few years back, Russ and Beth. So we have done quite a lot of work in the lab going back 3-4 years ago, exactly along the lines of what you are saying, Beth. But we can't change the game, because unless, let's say, either the hospital in Cambridge or some venture capitalist comes and takes this and does it, we don't have the tools as a research community to validate that. By building things like that, like the current one, we give tools to visionaries like Anders, and as Russ said, we hope that they take that forward, and in this way we move the needle a little bit. But thank you both very, very much.
Thank you.
Thank you for the very interesting discussion. And I will end by showing you what's going to be up next on Revolutionizing Healthcare. So in March, we will talk about artificial intelligence in oncology. And then in April, about actually what was just mentioned, the validation of clinical AI tools and how that can be done. And of course, the session will be up on YouTube soon, as always. And feel free to share it with colleagues, and also feel free to let colleagues know about the session such that they can sign up online. And last but not least, we mentioned it last time, but I will mention it again. This summer, we're going to have the second edition of the world's first summer school on AI and machine learning, specifically tailored to clinicians and healthcare professionals, over one prolonged weekend. And we really hope that you will be able to join us there to either start or continue your AI journey. And otherwise, thanks again to our amazing panel, and we look forward to seeing you next time.
Thanks a lot, Maribeth, Russ, and Anders for being with us.